what are we going to do this morning is finishing up everything before we quantize the fermions. And as I promised that I'll try to write down the building block. So remember that I claim that, well, not I claim. What Dan does is says, let's Taylor expansion. And it says, these are all the interaction terms in scalar theory. Good for him. And we're just going to find something that we can Taylor expand around. So we'll find all the fermion terms that is Lorentz invariant. Then we can just mismatch them together and stitch them all together, and we can write down all the Lagrange terms. So that's what I'm going to do in the next hour and the 25 minutes. But let's still recap. Recap is always good. What do we have done so far? Well, we have written down Dirac equation, and now I'll just skip all those parts. Says this is a good equation, meaning that it has all the Lorentz transformation property. And then what we showed, we spent on the entire Tuesday. I would say entire Tuesday we're spending on say that this thing is actually not the irreducible representation of Lorentz transformation. So you can split it into two parts, and these are both called Weil fermions. And these things has the property of being some projection operator onto the Dirac spinner, and then you get the Weil spinner. Okay, in this one, so this is in the Weil spaces, so it's very special. It just split up and like that. And in any basis, you can still do it by using a thing called gamma 5, which is hidden in this projection operator. So the other thing we learned is that funny thing is that if you take a, say, minus chirality Weil spinner, and you take this C conjugate of it, you realize this flip the chirality. So what they say is that you can take a Weil spinner, has two components, and then you flip its chirality and you add it together. Then it's almost trivial to show that you can try to flip it again, and you get it yourself. So this is what is known as a Majorana spinner. I don't know if I call him Majorana, if he's going to jump out of the grade. I have such a hard time to pronounce it. But that's the point, is that this thing has two components. But you just take a charge conjugate of itself and add it together. It's clearly satisfies this reality condition with quotation marks. And it has the right amount of component. So this combination is called the Majorana spinner. Okay, so the idea is Weil spinner is really good. It's a building block. You can use it to build the Dirac spinner. And you can use it to build the Majorana spinner. So this is what we have been done on Tuesday. Yeah? At the end of the Tuesday, I'm sure that you guys are all very familiar with this Lagrangian. Now, if you're not, but well, it's just the Dirac equation with a psi bar. So now that's that much more complicated. Okay, this Lagrangian, and you also have done your homework to find that the conjugated momentum is just this guy. I'll not write down that Hamiltonian because it's only relevant in the afternoon lecture when we quantize it. But I feel if I assign a homework, that you have 12:30 to 2 to do it, which is the 1-page long homework. You guys are going to kill me. So it's going to be very relevant to this afternoon, but not yet. Okay. Any questions? Today is the day to collect questions because this afternoon we're going to quantize this thing. We're going to do something quite different than just take all these spinners, manipulate. Then there's going to be accretion and annihilation operators popping out. It feels like a different part of the course. Yeah?
Just to clarify, the Majorana spinner is something that only exists in a certain basis? Or
no, it exists in all bases. It's just, so yeah, this is a good question. So basically we say for any Dirac spinner, we can define this. And then we're going to impose this. So this together define the Majorana spinner. And that C will change between bases. So in one basis, if it's a Majorana spinner, in all bases, it is. But it's just, on the other hand, it is special. Not all things can be called a Majorana spinner. It has to be a charge neutral one, which we'll see at the end of this class, that what a special property it has to have. But if it exists, suppose you found one, it is always the same real spinner in some sense. Okay, any more questions? You should ask questions, because if you don't, I have questions. So see, the thing is, I have this seemingly puzzle. Hopefully it's not really puzzling. We'll see. So first question is, how many degrees of freedom does Dirac feel? Question mark. Yeah? Pusai? How many degrees of freedom does Pusai have? Okay, this might be such a rush to jump to this question. Let's start with something hopefully you know. How many degrees of freedom does a scalar, real scalar field have? Huh? 1. Awesome. How many degrees of freedom does complex scalar field have?
2.
Excellent. Now come back to the question. How many degrees of freedom Dirac field have?
8.
To
start, it would have 8, right?
To start, very good. What happens eventually then? To start, it seems naively I would expect 8. There was 4 components, and we emphasize again without imposing any condition. It's a complex field. So naively, I would expect 8. 4 times 2 is 8. Solid argument. Okay, here is another argument. We have solved Dirac equation. How many solutions do we have? There's a U, there's a V, right? U and the V are different. But for U, you can choose Kasi equals 1 equals 2. So 2 times 2 is 4. Seemingly puzzle. I have 2 different ways of counting. By counting the solution, I'll just simply count. But Alicia has a point. It says to start, we have 8 degrees of freedom. So here's what happens. Is that go back to classical mechanics that David have taught you so well. Is that we're talking about literally Newtonic physics of point particle. How do we count the degrees of freedom? How many degrees of freedom a point particle, like this chalk, have? 3. Yeah, it can move in X direction, in Y direction, in Z direction. And what classical physics always do is call something phase space. And it says, I have to provide some position, and I provide some momentum. Not quantizing, they are all independent. Then they count. There's a 6-dimension phase space, hence there is 3 degrees of freedom. Yeah? solid argument. So what we claim is that the degrees of freedom is a thing we can count by counting the dimension of the phase space. And then divided by 2. This works perfectly well for scalar field. You have phi, and you probably still remember the conjugate momentum is something related to phi dot. They are completely independent, or 2 divided by 1, divided by 2, you get a 1. So here is what happens with Dirac field. Well, psi, as we count, to start, which is the position thing, has 8 degrees of freedom, 8 things. But what's the momentum? It's not psi dot, because it's a first order equation. With the momentum, we don't need a time derivative to specify. Instead, by calculating the conjugate momentum, we say this is the momentum that we're going to put in the phase space. Well, of course, it's also 8, except it's the same 8. We're not going to double count. If you count this complex thing as 8 real things, this is the same 8 real things. So the dimension of phase space is 8. And then you divide it by 2, you get 4 degrees of freedom, just like the number of solutions we have. And soon enough, we're going to see that, well, you did see in the tutorial that for U, you have one thing can call it a spin up, the other thing can call it a spin down. And then for V, it's the same. And this afternoon, you will see why do we call it one of them particle, one of the antiparticle. So in Dirac field, you can just say there is a spin up, spin down particle, and there's a spin up, spin down antiparticle. So there are 4 degrees of freedom. Everybody agrees. Okay. Seemingly puzzle number 2. Yeah? Okay, move on. Seemingly puzzle number 2. It seems that I keep saying that I can just grab 2 well spinner, completely independent. There's nothing like W plus and W minus are completely independent well spinner. And I would say if you have completely independent well spinner of opposite chiarly, you can just stitch them together. They're called a Dirac spinner. On the other hand, we also spend a whole tutorial to argue that this well spinner can't have mass because it has a definite chirality. It has definite handedness. Well spinner cannot have mass. But apparently, if you stitch 2 things that doesn't have mass together, you get a massive fermion. And the mass apparently shows up in the Dirac equation. Isn't that weird? Kind of weird. But we'll see. Okay, so let's start with the mass term, since this is the term we find puzzling. If we look at the Dirac Lagrange, it has a mass term also. And I can express by using the cool fact that they are complete. We can just express the psi in terms of the psi plus and the psi minus. Simple exercise. We're just going to plug it in. Okay? I take a few lines of each line should be trivial derivation, especially after you have done the homework. So then you should have psi dagger. So I'll take this dagger first and then take this dagger, but they are nice projection operators that are their Hermitian. So this is what happens to the psi bar. No, psi dagger, there is the gamma 0, and then I'll just write this down. Okay. I only did one thing. I split the psi into his 2 components. and then into the mass term. The mass term looks like this. Okay, now it's the seemingly puzzle thing, is that it seems I have 4 terms, but I don't. So let's do some inspection. It seems that I want to swap. Well, I guess it's easier to see to swap this guy. So if I swap, the gamma 0 will be combined with this to become a psi bar. It might be nice somehow. But let's just look at one term. It says, I want to inspect this term. See what happens. It involves some gamma 0 and p plus swapping, or p minus swapping. So let's just see what happens when I swap things. When I swap things, well, let's just write it out. Not terribly complicated. And well, the first term I'm swapping an identity, so it's still identity. The next term I'm swapping gamma 5. Well, it of course will change sign. Interesting. After I swap, it'll become a p minus. Which means if I had p plus, gamma 0, p plus, I can swap them and they become a p minus. But since our projection operator is really nice, they're orthogonal, become 0. Which means out of these 4 terms, only the ones come with the opposite projection operator will survive. If they are the same, there's a gamma 0 in between, the swap, they disappeared. Okay, based on this very inspirational discovery, we realize, okay, this term will survive, and so is this guy. Just to simplify the writing a little bit, this is exactly what we call the psi plus dagger, with the gamma 0 would be bar times psi minus, and then we have the psi minus dagger, and then we have psi plus. So this is what happens, is that the mass term indeed does not contain any terms that can be called a mass term for a single well spinner. Because if we have one well spinner, you kill the rest. There's no mass term, which is good. Agree with our argument that well spinners should be massless. And the mass actually coming from the interaction between the 2 halves of the well spinner. So you get one massless well spinner, another massless spinner. Together, they will interact with exactly the coefficient m, which provides the Dirac spinner mass. Okay, so well, let's just take a look at the other term, which shouldn't take long at all. So I wouldn't write much. Compare this to that. The difference is, in addition to a gamma 0, there is also a gamma mu. The only thing I care is about the swapping gamma matrices. So the rest doesn't matter. There's I partial mu, who cares? And then this argument, because they're going to swap twice. So it's the opposite. So it's actually what's going to survive is actually when they are the same chirality. Because of the extra gamma matrix. And this, indeed, is called the Lagrangian. This one term is called the Lagrangian of well spinner. with plus. So there are two kinds of well spinner. If you only have the plus type, you have this Lagrangian. And if you only have minus, you have that Lagrangian. But we can do one step further, says it's actually completely silly to work in 4 dimensions. I mean, the 4 components language. Because well spinner only have 2 components. So this is the time when we say, let's take special basis, which is the well basis. So then I can express psi plus just as W plus 0 and W plus dagger 0 times gamma 0, which is 1, 1. And there is a I partial mu somewhere. And there is a gamma mu, which is written as sigma mu, sigma bar mu. Okay, let me rewrite it so that's it's legible. So this is the psi bar, and this is the gamma mu, and this is the I partial mu. This is the psi plus. Two by 2 matrix multiplication, and then we only really need the first entry, which is sigma bar. So it's psi W plus dagger, sigma mu, I partial mu, W plus. So this is what well write down. This is the well Lagrangian in the 2 component language. This thing only have 2 components. And these are 2 by 2 matrices. So this concludes our discussion about the wells. Well, actually, no, we did. Sorry, I've been lying. But now we understand that why you will start with a massless Lagrangian. This is clearly massless. It only has a connector. But if you get another piece of massless Lagrangian and allow them to interact, you will make a massive Dirac spin. Interesting to know. Okay, so there is some disconnection, but we'll make the connection as time goes. So what I promised is we're writing down the building block of writing all fermion operators so that we can write down all Lagrangian. Okay, sorry, last sentence. If you just stick the Majorana spinner's expression in well basis, it's something like W. So a Majorana spinner is written as something like a W plus I sigma 2W plus star, something like that. If you just stick this into the Dirac-Lagrangian mass term, you see there's no problem. I have 2 chirality of well spinner. The mass term doesn't definitely exist. So you can just give mass to Majorana spinner. And for the kinetic term, you will just write down the equation of motion by using the Dirac equation, and then backward engineering to write down the kinetic. Okay, so now let's start the next topic. So between writing down all the terms, and the thing is we want to classify them because of the nature. The nature describes the particles in, like some interaction are very different from the other interactions. The weak interaction is very different from a strong interaction and electromagnetic. The weak interaction cares about the chirality of the spinner, for example. So that's why we want to not just write down the logarithm, but also categorize, basically in two piles. One of them cares about the chirality, the one pile doesn't. But in order to do that, actually, it's very interesting that we are actually going to talk about the discrete symmetry of, actually, we're only talking about one, so let's just say it. We're going to talk about the parity. So up to now, we have been hiding in the very safe corner around the identity of the Lorentz group. Because then we can tailor expand the study generator was like, hooray, everything works. Even if you can hide a finite distance. But actually there is one part of the Lorentz group. Actually you just can't reach by using our exponential map. It's just not connected to the identity, so we just fail. And this is what the parity does. So parity has a more friendly name. It's called a spatial inversion. So it's exactly what it sounds. It says if your time direction, nothing changes. In the spatial direction, you flip sign. So this, you can also, of course, write down in terms of our Lorentz transformation, it reads like this. And it's definitely not a hard task to check this thing. Will certainly preserve the length of the Lorentz length of a vector. Hence, it is definitely a Lorentz transformation. And we have no way to connect this thing to identity whatsoever. So we have to study it separately. Okay, see, flipping three spatial signs is hard. But we can simplify this problem a little bit by using the fact that as long as you are a Lorentz transformation that has been studied before, that is continuously connected to identity, then I know what happened. So here's we're going to do a silly demo by looking at me, and this is the x-axis, and this is the y-axis. And now I'm going to rotate 180 degrees. See what happens to x and the y-axis when I rotate 180 degrees. They flip sign. So I can say parity, too hard to study because there are three things. Flipping x's is not something we know how to study. And there are three of them. So first, let's reduce that number to 1. So this is a claim that a spatial inversion is nothing but no rotation around, say, z-axis. It doesn't matter. It's without loss of generality. 180 degree. And plus flipping the axis and rotating around. So that works. Then you can make a parenthesis as this is equivalent to flip x and y. Okay. So flipping one axis. This is good. This is related to our real life. Do you know anything in your real life you use approximately every day that does it for you?
Mirror.
Yeah, a mirror. So instead of studying this spatial inversion thing, what we actually want to study is called a mirror reflection. Then, okay, so how do let's ask a question. I have a Dirac spinner. How does a Dirac spinner transform under mirror reflection? I don't know. That's a good answer. I don't expect you to know. I say mirror reflection, but I still use P because there's a rotation by 180 degrees somewhere. So the question is, what happens if I have a Dirac spinner and I make a mirror reflection? I don't even know where to start. But we just learned this Dirac spinner is made of two little things that are called a well spinner. Well spinner is easier in some sense, because remember, we learned in the tutorial that it's definitely chirality, which also means it's definitely helicity. Something with a definite helicity, which means that it has a definitive momentum, angular momentum. That sounds like something we can study like classical, literally classical. So we're going to do the following thing. So we're just going to take okay, completely based on your preference. I don't care. But I'll take a right-handed spinner. Actually, maybe for me it's better to take left. Yeah, whatever. Take a well spin. We're just going to completely make it classical. And it says this is the thing that has, as we studied in your tutorial, it's basically this thing. Basically, it's a fist. If I identify the direction going through my finger as the angular momentum, going through my thumb as my momentum, my fist is a well-defined object that can describe well spinner. Yeah? Okay, here we're just going to do a group study do everybody have cell phone, computer, some electronic device? Yeah, do you want to play with it? Now is your chance. So please take your phone or whatever, turn it on to the camera selfie mode. I think that qualifies as a mirror. Yeah, your pad would work too, right? And then I want you to put your mirror, whichever is representing your mirror, in the, I don't know, you call that don't move your mirror. Choose a place to put your mirror, and that's your XY axis. Define as you wish. I don't care. But then hold your hand in a fist, whichever hand you choose. I also don't care. But then study how the angular momentum and the momentum defined as the fingers pointing to do in the mirror by pointing your thumb to the X, Y, Z, 3 directions. Okay? So I'm looking for answers in 3 directions. And each of them tell me what happens to the momentum and what happens to the angular momentum. Yeah? 6. I'm looking for 6 answers. Yeah?
The set doesn't change the momentum.
Depends on which orientation is your mirror. Your mirror is that way. Yeah? Yeah, because it's still pointing that way.
Am I measuring
Yeah.
with respect to me what I'm seeing?
Yeah, exactly. So this is your real hand, and there is your mirror hand, and you measure the relative thing. So for example, if I have a mirror, if this blackboard is a mirror, and I'm holding my hand up, and there is a mirror hand inside, I would say the momentum didn't change because it's still pointing up. And then I have to look at how my hands are curled to figure out if the angular momentum changes.
Yeah, it's changing.
It changes. Okay, 1 direction done, 2 more. Actually, there's two kinds of direction. But I'll just say, by completeness, if you study X, Y, Z 3 directions, we're definitely good to go. There are only 3 directions for movement.
Yeah, like this.
Yes? If you want to make some noise in class, this is also the time to make noise.
Yeah.
It's like that.
And you are also free to move around if you see somebody has a bigger mirror.
Z and Y.
I guess because that in there, if you point it like
Yeah,
this,
yeah.
real life is pointed this way,
Yeah.
the mirror is
Yeah,
that way.
yeah. But that means the momentum flip.
Yeah,
What happens to the angular moment?
it's the same.
It's the same.
It's the
Ah,
other person's doing it the other way, so it's like
This.
we flipped the momentum.
If you're going to Z,
Yeah.
unless you're going this way.
Oh, wait, all directions, right? No, except for at this way.
Yeah, it's what, yeah, you.
Because angular momentum is the same in X, right? Oh, yeah, that's right.
So you're not inverting all your, it's not parting, it's just mirror. So if you're changing, this is the CX, yes.
Yeah, if I go this
Marker is pointing that way and from is pointing this way.
Oh wait, if you do it,
Also, it's
if you do it this way,
No, it's just mirror reflection. It's just flipping the CXs. Still you have to do a rotation around.
yeah, I mean the way the first is Z shape.
Because we're not changing X and J,
So many
changing
momentum,
X. So we have to do a 180 rotation.
angular momentum.
So it would be parity.
I mean, we need to rotate.
Yeah, of the C, no, X and Y. Because in here we're just seeing how set is.
And that's when P sets it to minus P sets. No, I think it should be minus, yeah.
But in here,
Hmm,
it doesn't-
yeah.
Oh, no, because you want to use your right hand again. Here, too.
Okay. Do we have conclusions?
yeah,
Seems we're quieter, so let's hear the conclusions. Yes?
so in the axis that is reflecting, that is perpendicular to the mirror,
Uh-huh.
the linear momentum changes,
Mhm.
but the angular momentum doesn't change.
Uh-huh. That's this case.
Yeah.
Okay. Yeah. I say my drawing skill is questionable at the best.
And for the other two, the linear momentum doesn't change,
Mm-hmm.
and but the angular momentum does.
Uh-huh, very good. So, as she says, this one should change.
And the selfie mode.
So this, like, I feel if I just draw this, impacted by my poor skill of drawing, it might not be as clear as you just look at it yourself. But the conclusion is something will change and only one thing will change, no matter which direction you do. And remember, our helicity is defined to be the projection of the angular momentum in the momentum direction, which means if only one thing changes sign, which means the helicity will change, no matter what you do. So in a mirror, but for wire spinners, helicity and chirality is the same thing. So that means mirror times parity will flip chirality, because who cares about the rotation? The rotation doesn't change chirality anyway. So what we realize, if you started with a left-handed spinner, it would become right hand. And if you started with a right-handed spinner, it become left hand, which is our everyday life experience that in the mirror, your left hand looks like a right. Anyway. So it all makes sense. So now we can finally answer our question. What does this do to a Dirac spinner? So this is just another way writing time doesn't change, space change. This is defined to be that. So now we have some knowledge, is that the left-handed spinner will become right-handed, the right-handed will become left-handed. So basically, we want to flip the top part and the bottom part of the Dirac spinner. What should we use to flip it? Huh?
Like a big sigma X.
Gamma 0.
Gamma 0 would fit the bill. True. Remember, gamma 0 is this thing.
Okay.
Actually, there is a sign. I'll post something so you can understand the sign, because if there's no way we can determine the plus minus. On the other hand, you can check this thing is pretty nice. If you do it again, it can go back to itself. If you flip the space twice, your Dirac spinner becomes itself. It's a good thing to happen. Okay. Last thing we'll just check. Now we have this thing, which is called the parity transformed Dirac spinner. I feel you should know what I'm going to say. Now we have a transformed spinner. We should check, does it satisfy Dirac equation? It's just a sanity check. Okay. So the Dirac equation for this guy, we have to be a little careful that I'll put a little prime here to indicate we're doing the derivative respect to the minus sign. And then the mass term doesn't care. So we wonder if this thing equals 0. This is the Dirac equation for a spinner with the space all flipped. So let's just write it out. Prime. And then doing derivative on the minus x is like doing the derivative on the x, but the change of flip a sign. And now I'll use my formula says under parity change like this. So I have that. And the last thing to do is to commute this gamma 0 all the way to front. The first term, nobody cares because it's gamma 0 and gamma 0. The second term we do care because it's a different gamma, which the anti-commute. And now the overall gamma 0 is in front. But this is exactly Dirac equation, which is given to be 0. So indeed, nice thing that we figure out how parity will change our Dirac spinner and how this parity change the Dirac spinner is still a Dirac spinner. So now we understand, because parity change chirality, remember that I said that all the interactions has two categories. The weak interaction cares about the chirality. The other interaction doesn't, which means now it basically says the weak interaction doesn't preserve parity because the character changed. And the other interaction That's preserved parity. So now after we write down all the possible terms, we wonder how they transform under parity. And there is the parity conserved ones. We can use those to build up the interactions conserved parity. And then we have the parity violating ones. We'll use those to build the violating. So I think we can take a break of 5 minutes.
Right, because that's what you should have. Or no, that's what we So we don't get like minus.
Well, we get integrated.
Yeah.
Sí, o sea, hasta que llegaste,
I mean, this one's
pasa. Y entonces los que son by spinners,
It's in a certain basis.
Depends on the direction of the momentum.
no vimos eso. Ah, bueno, no sé si lo vieron ahora. Entonces, by spinners, así es como se puede construir un mayoral. Pero en general, en cualquier basis pones estas condiciones y así es como encuentras cómo construir mayoral.
That's the exact opposite response I got from literally.
Y es
Also, do sampling and do
Son Pearson now.
vieron la clase. Entonces nada más vimos otra vez el lagrangiano, y después no sé si vimos cuántos degrees. Para empezar, es un entonces para empezar, y después
parity another time.
mecánica clásica.
If we hope that it's simple like this.
Este tiene 8 componentes, pero
With these connections to the propagators, right? You have these as well.
Even if you have twice, you still have this twice. So you can imagine that.
Pero David y luego aquí, bueno, como todas las teorías gauge que tengan un, bueno, supongo que solamente se valen grupos, pero bueno. Luego vimos este término, ya ves que en el tutorial vimos que los espinores que tienen una helicidad definida no pueden tener masa.
The job was going to follow the request.
Preguntamos cómo es que tenemos un término de masa en el canal, si estos los estamos descomponiendo en bytes y estos no tienen. Y entonces,
I was like,
I mean, these ones.
un espinor de Dirac en un espinor de y entonces nos dimos cuenta de que ya no realmente en términos de byte lo que aparecen son términos de masa que mezclan, o sea, bueno, son términos que traen una N, pero que mezclan psi más y psi menos. Entonces no podemos, eso no es realmente un término de masa para los espinores de byte. Es un término de masa para el espinor. Y entonces empezamos con 2 espinores massless de byte que tienen helicidad definida, y el lagrangiano de Dirac lo que hace es que los hace interactuar y obtener un massive Dirac. Sí, por eso. Y sí, sí. Los términos cinéticos sí se comportan, o sea, que realmente es un término cinético. Descomponiendo ahí acá. Y
You have until
luego
what hour?
Sorry?
You have until what hour?
ok, entonces parity, pues nada más es cambiar el signo de X. Y ya nos dijo que esto es algo desconectado de y entonces, bueno, nos mostró físicamente que una inversión en X y Y es rotar primero los ejes en en X y Y. Y luego cambia Z. Y por eso es que este cambio de Z es lo que se llama mirror reflection. Y eso era lo que estaba solamente cambios
¿Y por qué tomaban mirror reflection como si fuera?
No, o sea, primero, parity es un caso particular es cuando, bueno, parity, una forma particular de descomponerlo es como cambiar primero rotar alrededor de ese caso y cambiar Z. Entonces, por eso es que analizamos cómo se comportaba solamente mirror reflection. Pero luego te das cuenta de que rotar alrededor de Z, bueno, si escoges tu dirección en la que se está moviendo la partícula como de Z, entonces la helicidad solamente va a depender de ese flipping en Z. Y por eso es que solamente la parte de flipping es
That's on video.
You figure if you're a mirror line, you need to go any farther.
That's insulting.
I'm gonna say this.
What's bad about it?
Listen that to you once.
Okay, let's get started again. So now we have a parity thing, which is the way we're going to use to classify things. But let's say what things I want to classify. Well, let's start with the good Lagrangian terms we already know. We know this guy. Just stripping off the things. The Kinect terms basically look like that. It says if you have this is Lorentz good, Lorentz covariant. Then you can just attach a partial derivative on it to contract the index to make it a scalar. As a good scientist, I'll follow the induction rule, right? What forbids me to just keep going? I can just do this. Yeah, you like my logic? You can just keep going. People are laughing. Why?
No.
Stop. Very good. I hope somebody will stop me. And I hope it's not because I'm being annoying. But that's also good. If I'm being annoying, lecture, let me know. I'll stop. But yes, I should stop. Why? Precisely at this line, I should have stopped. Why?
Because there are only 16 independent quantities like that.
Oh, you are like so far ahead. You're like 15 minutes ahead, 10 minutes ahead. No, it's good. No, it's good. Keep in mind the number 16 is very important. But let's come back just to this line. Why there is no point of writing down this line? How many gamma matrices I have? How many indexes I have here? Using pigeonhole theorem, I have to at least have one pair. Somehow I want to say one pair of socks. But we actually at least have one pair of gamma matrices. And because they can all commuting and anti-commuting, you can always bring them together. And they disappeared. They turn into 1 minus 1, who cares? So there's no point of writing this line. So very good that I was stopped. Good point. Okay, using the same logic, we come back to this. That, okay, I'm writing down 4 indices. But there's only 4 indices. There's really no point of writing this down. I could just write down gamma 0, gamma 1, gamma 2, gamma 3. Everything else I write down would be something lookalike. There's nothing I can write independent of this. And I hope that you recognize what the hell is this thing, right? After like spending, I don't know, many times commuting this like all the time. So this thing is nothing but the psi bar gamma 5 psi with some I or whatever coefficient. But there's no other independent things I can write down. Yeah? Then we can go one line above. Now I have 3 indices. It's like the thing, if you can write down to things with in 3 spatial dimensions, if you can write down things in 2 indices, it's actually equivalent to the other thing. It's the same logic. All I could be really, really fancy says that I can write this very fancily as with some like Levi-Civita simple. And then says this thing, look, it only have 1 indices left. And actually, gamma 5 has a really pretty way of writing it. Okay, I can't remember the I's, and there's probably is I, but you can check that the gamma 5 we're so familiar with, it's exactly this, with a factor of something like a 24, because there were 24. And each of them is exactly the same, and there were 24. Which means that this thing, you can contract it with this Levi-Civita center and basically make a vector out of it. And then, so we'll say this guy is nothing but psi bar gamma 5, gamma sigma psi. So there are only 4 degrees of freedom. Now you can also count as 3 indexes object. Remember, we want them all to be different. You can only make 4 different things out. Okay, now we're almost done. This guy, it basically says the anti-commutator of that is eta mu nu. It doesn't give me new thing. So what gives me new thing must be the commutator, but I know the commutator is just my Lorentz generator, which is a 2-indexed object. So, okay, this is a little messy. Let's reorganize them for how many index they have. Okay, so that's all we have. And we are using a complete list method. Somebody stopped me very rightfully when I try to keep going because I'm not going to get new stuff out of it. And now let's count. Okay, maybe not 15 minutes. But let's count. How many terms do I have for the first line? 1. I know some of my questions are like that. No, it's also in interview. Sometimes you might think my question is too trivial, but continue answering me. Okay, the next line. Now there's a gamma 5. How many degrees of freedom?
1.
Still 1. All right, now we have non-trivial number of degrees of freedom. 4. And this one, okay, you just tell me gamma 5 doesn't change anything. How many Lorentz generator we have? Wait, that's the question asked the very first class. 6. And now if you add them up, you get this magical number called 16. Why we should be so happy about the number 16?
They're 4x4 matrices.
They are 4x4 matrices.
So we have to have 16 number to specify a general 4x4 matrix.
Yes, it's a good point. We started with two 4-component stuff, so we'll make 16 things. All right, so here we go. These are the building blocks of how fermions interact. any fermion interaction you can ever written down, because we want to respect the Lorentz symmetry, we always utilize some of them. And now you can just mix match them together, and now we're going to classify them. And using the parity. Okay. It's not complicated. This guy says this guy goes to gamma 0. Yeah, it's good to know. Let's see what happens to gamma dagger then. Well, it goes to gamma 0 dagger, gamma 0. Sound logic? I'm just taking a dagger off of the thing we just discovered. Right? Okay, very good. Now I can figure out what's my first term transform. It says psi dagger will become psi dagger gamma 0. Okay, let me do one more step, since this psi bar is everywhere. Dirac conjugate is very important. Okay, one of your interview questions is, why do we need a Dirac conjugate? I'll upload to the questions tomorrow after lecture. Okay, so if I want to ask what happens to psi bar, we get another gamma 0, but then I get a psi dagger. Okay, now we're ready to see how the Lagrangian terms do. So we have psi bar psi goes to psi dagger, gamma 0 psi, but these guys combine back to get a psi bar. We find out that this guy doesn't change under parity. It's a scalar. Sometimes we can call it this is a true scalar. It doesn't change under Lorentz transformation, doesn't even change under the discrete Lorentz transformation either. Well, now let's look at the next guy, which says has a gamma 5 in between. So then we have the psi dagger, and the gamma 5 just stick around. Psi goes to gamma 0 psi. And now we need to swap things to get the psi bar back. And when we swap, we'll pick up a minus sign. So you realize this thing looks like a Lorentz scalar to us, but secretly it's not if you consider the discrete symmetry. So this is known as the pseudo-scalar. And the pseudo is trying to point out that it actually flips on and parity, which means it doesn't conserve parity. Okay, now we can write down this is just like this, except I swap gamma 5 for gamma mu. So we have this thing. And now there is a condition. If it's time component, the swapping is just fine. It's the space component that it will pick up a minus. Okay? It's different. But that's what we expected. We have a vector. Okay, I think I tried my best to persuade you that X is not a vector in general relativity interview, but well, we never go to curved space. In Minkowski, X is still a perfect vector, and at the parity, X goes to T minus X. So this is actually exactly what a vector should behave. So this thing is called a vector. Okay, I think it's kind of silly for me to do this because it has one more gamma phi, which just means you have some swapping and pick up some minus sign, which means this guy will behave exactly opposite of vector, which is somehow called the axial vector. And if you're patient enough, you can check this thing is a tensor. So that's all we have. And this is parity violate. And this, as you would learn in standard model, is what describes the weak interaction. And this, since it doesn't violate parity, we will learn from this course by QED, the quantum electrodynamics. And by the next course, you will learn about non-abelian gauge theory, QFT2. There's a week, it's all about it. Okay, so now we have all possible fermion building block for interactions. Then we have all the Lagrangian we will ever need it. Isn't that nice? Next topic, well, same topic. We're actually going to build a thing today. We're going to build a, since this one we can't directly use, it carry all these indexes from. This is our mass term, this gives us connect term, but we can't directly put it as Lagrangian density. It's not a scalar. Yeah?
Does someone use the last term, the tensor, for something?
Good question. I've never been so curious. I'll check it. I'll check it if anybody. If you just stitch this thing with the other guy, somebody should use it. I guess if you stick this with itself together, that's the for fermion interaction. But no, I haven't thought about this. Let me think about it. I haven't seen it, but somebody must have used it because we like to exhaust all possibilities. Okay. So next question. Next thing. Well, we'll follow the same route that we were talking about the symmetry. And let's continue to talk about symmetry. And we'll talk about the global symmetry that you guys are familiar with, because I asked for the current density in the first homework. But let's just review it again because it's the best theorem ever, right? You saw like 5 versions and then continue give you more versions. I'll follow Dan's version. Dan's version says that something like if you change psi is our field, he changed the phi. But if you change your field in some way, and if your Lagrangian is changed by a total derivative, then you can write down the current, which is equals to partial L partial mu psi. And times this y thing minus. Yeah? So this is just Noether's theorem. That's the definition he gave. Okay, now we're going to do the same thing as he does. Because if you look at our Lagrangian, which is nowhere to be found, it doesn't take long to rewrite the advantage of not teaching standard model. It's just this. And then says, let's do this again by thinking about the psi has some global phase thingy. Then it should be obvious because psi diagonal psi change in the opposite way that Lagrange is invariant. Yeah. So the only thing I need to work out is the infinitesimal change of psi, which by now, sorry, where is the field? By now, you should be very familiar with this linear expansion thing. Then I identify my y is minus I alpha psi. And I can stick it in the current definition, which gives me psi bar I gamma mu. And I want to replace the y psi thing by minus I alpha psi. And then it gives me psi bar gamma mu psi. And alpha is an infinitesimal parameter, we just throw away when we got the current. And then now we can look at this charge we can define, which is the integral of the spatial component, which we show it's indeed a psi dagger psi. Dirac is very happy when he sees that. He says, oh, look, my density psi dagger psi. That's positive definite. Hence, we have a happy Dirac. This is completely ridiculous. Okay, now I'm here. So, yeah, Dirac is happy. He gets his conserved charge of density, and then the density is even positive definite. He was very happy. And the next thing we're going to do, what I call is the QED. I'm sure somebody will be able to pronounce this better, called a Amoos-Busch thing. Okay, the first taste, we'll just write down the Lagrange, and we'll come back to it until like the last slide. So remember, we write down all the possible terms, and we know that the QED is going to use the vector because they respect the parity. What can we do? Yeah, we have a vector type of, actually, vector type of current. What do we do? How do I make it a scalar? Because Lagrange densities are scalars. Yeah. What do I do? Question mark. With
a vector.
Yeah, with a vector. Excellent. Which vector do I pick? The potential? Like this one? Well, indices are contracted, so we proved that the other thing is a vector. This is a vector, contract two vectors, get a scalar. Sounds very legit. In some sense, it's right. Well, of course, there's in some other sense. Okay. Why do I say in some sense? What could go possibly wrong by writing down this Lagrange? Yeah. Gauge invariance. That's a great vary. I used to have this symmetry. Okay, symmetry is a misnomer, but we'll get to that next week. I used to have this awesome symmetry, and this term clearly breaks it. Unless, well, okay, so I have a term that has a mu, says a mu transform, and it clearly produces some term that doesn't disappear. Unless, if we stare at this term, or some other terms, but there are two kinds of things we have now. Now we have a vector potential, we have fermion. We change the vector potential. Well, vector potential always have this gauge symmetry, and we did the change says crap. We break the gauge symmetry. So what's the obvious fix for that? Vector fermions, change the vector. Vector change. Fermions. Let's change the fermions too. So fermions should also change, so that hopefully the change from the fermion would cancel this extra term, right? Makes sense. Okay, which means we're introducing something called a gauge the global symmetry. So we do have a global symmetry. Says psi goes to e to the minus I alpha. Psi is a symmetry we just showed. It's a good symmetry, and they even give us a current, as Nurser tells us. So what do I mean by gauge the global symmetry? It literally means, remember you have a global parameter? Let's make it depend on the space-time. That's all we meant. But just for good measure, we'll throw you in some proportional constant and say, like, determine it later. Okay. So now let's say what happens. Well, what happens to this guy is, well, nothing happens. I can just write down how Daiger transform. It really doesn't help. It still cancels. But which term will help us? The kinect term, if there's some derivative. Before we're just doing the derivative. Now that we have something else to do the derivative on. Okay, so let's say what happens to this. Okay, I'll say the partial bar will have a gamma 0, but they will combine with this guy to give you again partial bar. And this thing is not very helpful because it will be canceled by the other transformation. So the start of this Lagrangian still give you psi bar. Okay, so now I need to do the partial derivative. The partial derivative acting on psi Daiger, acting on psi is going to give me the term. Okay, let me just write it. There is a term called psi mu acting on psi, and then there is the other term, which is psi mu when it's acting on the exponent, which gives me minus IQ partial nu alpha. And then, yeah, whenever exponents show up, they will all cancel. So I just didn't write. So this term, well, this term is what it is before, but now I have this extra term. This extra term is given by psi bar, gamma mu, I and the minus I cancel. Q partial mu alpha psi. Okay. So this says, and this one has the extra term of psi bar plus partial mu alpha x psi. Gamma mu. So if we compare these two things, we realize we'll be okay if the interaction comes with a strength of minus q. Then minus q times this plus q times this, they will cancel. So actually this q was important. This is how strong the interaction can be. And it says it can't be anything. It has to be proportion to minus q. So the interaction is given by psi bar minus q psi bar gamma mu a mu psi by require gauge symmetry. So now let's just try to combine things together. So before, I have I gamma nu partial mu psi. And now I have minus q gamma mu a mu. And the idea is we want to take this I gamma mu out. And the right is mu plus I q a mu okay. The idea is we still wanted to write it as a kinetic term. So if we define this thing to be d mu, we can combine the interaction term and hide it inside the connector. And you're like, okay, what's your point? You make your Lagrange shorter for sure. So that's just the Maxwell theory. So this is the QED Lagrange. And we get to there by taking the term that can interact with the vector potential and use gauge symmetry to fix the interaction strength. So that the Q that we figured out, that is called some sort of density, now it has a better name. It's the charge density, which is the electric charge density. And the Q is the electric charge of the fermion. So this tells us different species of fermion interact with the photon differently. It depends on their charge, which is true in our world, which is good. And one more thing about this d mu, it's called the covariant derivative. And the most important feature is that this process, what we did here to fix how this d mu needs to look at, is universal. It's called the minimal coupling. So if you want to couple a gauge theory with your fermion matter, like electrons and such, it's like in GR. Remember that the minimum you think you do, you just change pressure mu to covariant derivative, and you get a GR theory, or you change your metric too. But in this, it's the same. You just, whenever you have an interaction, gauge interaction, you just change your partial derivative into covariant derivative, and all the interaction will be taken care of to be respect to the gauge theory. It's neat, isn't it?